If a function is Riemann integrable, then it has to be bounded. The reason, here's the proof. Let's recall the definition of Riemann integral. For example, we're given a function and we draw its graph, x, y. Integrate from a to b. Here's the graph, roughly. So it's like we have this curly trapezium, right? That's the top of the trapezium, bottom of the trapezium, the height of the trapezium, and the other side of the trapezium, right? It's like this trapezium. So, in other words, we want to find out the area of the trapezium. It's like we can just approximate it by partition this interval into many, many small intervals. It doesn't have to be even partition at all. So, first point A, second point x1, next point x2, all the way, right? Let's say we have n different small intervals. And then the way we can approximate the area is that we can, first of all, calculate the area of each small slices, right? The first slice, second slice, and so on. And so for each slice, we can just roughly treat it as a small rectangle. Right? For example, this slice in the bottom of the rectangle is just x2 minus x1. We call it delta x2, right? And what's the height? Height is just f. So remember the definition of, so it is the limit modulo p approaches 0, sigma I from 1 to n f of c I times delta xi. So f c I, for example, in the second interval, I have c2. c2 is roughly the height of the f of c2, right? Functional value is roughly the height. Then we have bottom delta x2, bottom times height. We have the roughly the area of this small slice, right? So we have to use the sum, right? We add up all the small slices, then it's approximately the area of this curly trapezium. Now, the point is, how do we approximate it as close as possible, right? Accurate as possible, is that we want to partition this AB into many, many, many small intervals. How can we make sure that each small interval is small enough? All we have to do is to make sure that the biggest small interval is small enough, meaning we let P modulo approach 0. Remember, P modulo represents the width, represents the width of the biggest small interval. Right, xi minus xi minus 1, the maximum. As long as the biggest small interval is small enough, then all the other smaller intervals, of course, will be smaller enough. In other words, we can make sure, as long as the partition is dense enough, then we can hopefully approximate the area of the curly trapezium by adding up the areas of each small rectangle, right? We can make sure it's as accurate as possible. That's what it means. And so since we assume the function is Riemann integrable, that means the limit exists, right? Let's say the limit is I. This time I is a fixed constant. So it says following the definition of the limit, it says for any epsilon that's positive, there exists a delta that's positive. As long as the modulo P is small enough, smaller than delta, then the absolute value of the sigma I from 1 to n of f of Ci times delta xi minus I can be small enough, right? So what it really means is that as long as our partition is dense enough, meaning as long as the biggest small interval is small enough, right? That's what it means, delta. Delta means small enough. Then the absolute value, it means the Riemann sum, right? The rough area, meaning the sum of the little rectangles. It's a rough approximation, can be close enough to our precise area of the curly trapezium. Their difference can be small enough, right? So that's what it means by absolute value, right? Their difference, their distance can be close enough. Right? So since it works for any epsilon, then I can choose a specific epsilon. Let's just choose 1. Right? For this specific epsilon, I can find a delta. Of course, delta is associated with the given epsilon, right? So there's a delta as long as the biggest small interval is small enough. Then we can make sure that their difference, right, their distance can be small enough, sigma. Of course, the partition here is also associated with the given epsilon, right? For different value of epsilon, we may choose different partitions, right? I from 1 to n minus I can be small enough, smaller than 1. In other words, if I just get rid of the absolute value, then I can have epsilon sigma I from 1 to n minus I is smaller than 1, bigger than negative 1. In other words, sigma I from 1 to n is smaller than I plus 1, bigger than I minus 1. Right? So in other words, if I just split the sum into, first thought, the sum into the first item, that is f Ci 1 times delta x1, right? That is the rough area of the first rectangle, right? Delta xi is the width. F Ci1 is the height, approximately, right? The area of this small slice. Plus, the remaining sum is sigma I from 2 all the way up to n is smaller than the same thing, I plus 1, and bigger than I minus 1. Right, then I can just minus this part on every side. I have f of Ci1, in this case, Ci1, the first Ci in the first, the x value in the first interval, right? Delta x1 smaller than I plus 1 minus sigma I from 2 all the way up to n, bigger than I minus 1 minus sigma sum from 2 all the way up to n. In this case, notice that Ci1, according to our definition, right, the choice of Ci in each small interval is just random. Right? So here I can choose any Ci1 in this first small interval. Right? I can choose x to be the left edge, right edge, the middle point, anything, some random point in the first interval, whatever, doesn't matter. But delta x1 is fixed, right? So fixed, 1 is fixed, fixed epsilon, that's 1. We found a fixed partition, right? It says any partition is fine as long as the partition is dense enough. Then we've found a fixed partition, specific partition, we made sure that the biggest small interval is small enough. In that case, then the width of the first small interval is fixed, denoted as delta x1, right, in that case. Now, so that means whatever value of variable I choose in the first interval, then I multiply by the fixed width, right, is always bounded in between two fixed numbers, right? I is fixed, 1 is fixed. Sigma, sum from 2 to n, is also fixed, but notice that the n, right, the number of small intervals also depends on the given epsilon. Since here the 1 is fixed, therefore, like I said, I've chosen a fixed partition in this case. So n is fixed, associated with 1, but it's also fixed. In that case, for sigma from sum from 2 to n, f of Ci times delta xi, right? Remember, like I said, that the choice of Ci in each small interval is random, right? It's free for you to choose. And for each, delta xi is already fixed, right? My partition is fixed. So, since the choice of Ci is random, it's for free, then I can just fix Ci in each small interval, right? For example, in this small interval, I'm allowed to choose any random Ci, right, inside this small interval. However, since the choice is random, right, even under the random choice, the inequality remains true, right? The limit always exists. The inequality always remains true, even if the choice is random. Then if I fix Ci in each small interval, does my inequality still remain? Of course, yes, right? So therefore, I can just, in each small interval, I will fix Ci. Now, remember, now Ci is fixed in each small interval, right? So f of Ci is also a fixed constant in each small interval. And also, for this fixed partition, the width of each small interval, delta xi, is also a fixed constant. So therefore, I have a constant times a constant, still a constant, for each member of this sum, right? Each member is fixed constant. So, like I said, even though n, the number of partition, is associated with the given epsilon, right? But it's already fixed, right? Once given epsilon, it's already fixed. It says any partition. I said fixed partition also works, right? Any partition works, and fixed partition also works. So I have a fixed number of sum. For each member, it's a constant, right? So I have a sum of finitely many members in which each member is a constant. So this sum has to be a constant, right? Has to be a constant. Let's just say M0, right? Constant. Of course, associated with the given epsilon and associated with the fixed partition as well. But anyway, this is a fixed number, right? So in other words, I plus 1 minus fixed number is also a fixed number. Right? So is this. So in other words, if Ci1 is fixed, right? Fixed number times a fixed number. So Ci1 is, what did I say? Ci1 is random, right? In the first interval, choice is Ci1. It says any Ci works, right? So Ci1 is random to choose, right? So for any value, any x value in the first interval, if I use the function value times the width of the first interval is always bounded in between two fixed constants. Right? So in other words, can I find a large enough constant that's even bigger than this fixed constant? Yes. So that is smaller than m1. Right? M1. M1 is fixed. And this, can I find a small enough number? Right? It could be positive, it could be negative, but can I find a small enough constant that's even smaller than this? Right? I say yes. So I'm going to still use minus m1. Right? It's achievable because I can find a big enough constant that's bigger than this part. Right? Also, for this part is also fixed. Therefore, if I just choose m1 to be big enough, then somehow I can say that m1 and minus m1 can be, at the one end to be less than that. At the other end can be bigger than that. It's always doable, definitely achievable, right? So m1 minus m1, in other words, if I use the absolute value in this case, what do I have now? Of course, I have first, I have to divide by delta x1 on both sides, right? The fixed number, right? Divide by delta x1, right? Divide by delta x1, right? Divide by delta x1. Right, then I use absolute value. Absolute value of f of c1 is less than m1 over delta xi. Let's just call it m, right? Minus m, so m positive, right? M is positive. Fixed constant. And also remember, like I said, the choice of ci is random. So in other words, no matter what the value of the variable is, my functional value is always bounded by a fixed constant, right? In the first small interval. And so likewise, we can easily show that the functional value, no matter what the variable is, functional value is always bounded in the second interval, as well as in the third interval, and so on and so forth. Right? For this fixed partition, once I'm given the fixed epsilon 1, right? It says any partition is fine as long as the partition is dense enough, right? So I'm just going to fix a partition and make sure that the partition is dense enough, right? So meaning the partition is fixed. Each small interval is also fixed. In each small interval, I can easily show that following the same logic, the functional value is always bounded in each small interval. In other words, overall, the overall interval AB, my functional value is always bounded. Right? So that means, so in other words, in order for a function to be Riemann integrable, a minimum requirement is that it has to be bounded. So in the future, every time we see a function that is unbounded over a some interval AB, right? If we somehow find that the function is has some problematic point, like, for example, at its left edge, right? The problematic point where the function is approaching positive infinity or approaching negative infinity around this point, then we can immediately claim that the function is not Riemann integrable over this interval. I'm talking about proper integral, right? If it's improper integral, it'll be a different story. Maybe convergent, maybe not.